Welcome to The Explainer. All right, today we are diving deep. We're going to take an advanced look into the truly complex and honestly fascinating world of irrational numbers. Okay, before we jump in, just a quick heads up. This is our advanced explainer, so we're assuming you've got a foundational understanding of number systems. If you're looking for something a bit more introductory, we actually posted a simpler version just a few days ago. You might want to check that one out first. You know, our story here doesn't start with a nice, clean definition from a textbook. No, it starts with a full-blown crisis. There's this legend about a mathematician named Hippasus. And get this, the story goes he was thrown overboard by his own colleagues, the Pythagoreans, all because he discovered something that completely shattered their perfect, orderly view of the universe. And for the Pythagoreans, this wasn't just a math problem. It was a philosophical catastrophe. I mean, their entire worldview was built on this one beautiful idea: all is number. They believed that absolutely everything, the cosmos, music, life itself, could be explained perfectly using whole numbers and their simple ratios.
See, for them, numbers and geometry were two sides of the same coin. They saw the universe as this perfectly ordered system of commensurable quantities. That's a fancy word, but it just means everything was measurable. They thought that for any two lengths, you could find some tiny, tiny unit that would fit perfectly into both of them, like a universal ruler.
So what happens when you find a length that breaks that rule? What if you find something that can't be measured by any common unit, no matter how small you make it? That was the catastrophic question. And you know where it came from? Something so simple: the diagonal of a basic square. Turns out that one line was incommensurable with its sides. And that single discovery opened the door to a whole new and, frankly, terrifying kind of number. Right. So this crisis basically forced mathematicians back to the drawing board. They had to look way closer at the fundamentals and come up with a much more rigorous definition of what a number could even mean. So let's start with what they thought they knew. A rational number, right? It's pretty straightforward. It's any number you can write as a simple fraction, p over q. Think of things like 1/2 or the number 5, or even a decimal that stops, like 0.25, or one that repeats in a nice neat pattern, like 0.333 forever. Clean, tidy, predictable. But the contrast with irrational numbers, wow, it is stark. Irrational numbers are basically defined by what they aren't. Their decimal expansions are just wild. They go on forever and ever, and they never settle into a repeating pattern. It's pure chaos. In a very real sense, you can never ever fully write one down. And the number that probably kicked this whole thing off was the square root of 2. That's the length of that diagonal we were talking about. And the proof that it's irrational, it's just a classic. It's such a beautiful and elegant piece of pure mathematical logic.
So let's walk through it. We're going to use this really powerful method called reductio ad absurdum, which is just a fancy Latin way of saying proof by contradiction. The strategy is absolutely brilliant in its simplicity. You start by assuming the exact opposite of what you want to prove. Then you just follow the logical steps until the whole argument completely collapses on itself.
Okay, so here's our starting point. Step 1, we're going to assume that the square root of 2 is rational. We'll say, sure, it can be written as a perfect fraction, p over q, and let's say we've already simplified that fraction down as far as it can possibly go. Now, if we square both sides of that equation, we get 2 equals p squared over q squared. A little rearranging gives us p squared equals 2 times q squared. And right there, that tells us something crucial. P squared has to be an even number because it's 2 times something. And here's a key rule in math. If a number's square is even, then the number itself has to be even too. Okay, so p is even. This is where the logical chain reaction really kicks in. If p is even, we can write it as 2k, right? 2 times some other number. Let's substitute that back into our equation. A little bit of algebra later, and what do you know? We find out that q squared also has to be an even number. And if q squared is even, well, then q itself must be even too. And wait a minute. Hold on, this is the big moment. We started this whole thing by assuming our fraction p over q was in its simplest form. But we've just logically proven that both p and q have to be even. If they're both even, they can both be divided by 2, which means our fraction wasn't in its simplest form after all. That's the contradiction. The whole argument falls apart. And that means our initial assumption. It has to be false. The square root of 2 simply cannot be a rational number. Boom. So the discovery of the square root of 2 really just opened the floodgates. It was the first crack in the dam, and it revealed that this world of irrational numbers was, well, it was way larger and a whole lot stranger than the Greeks could have ever imagined. And it turns out these irrationals fall into two main categories. First, you've got your algebraic numbers. The square root of 2 is one of these. You can think of them as being the tame ones, in a way. They're the solutions to relatively simple polynomial equations. But then you have the transcendental numbers, and these are the really mysterious ones. They can't be captured by any of those polynomial equations. And the most famous transcendental number of them all? Well, of course, it's pi. You know it, the ratio of a circle's circumference to its diameter. Now, we all use approximations for pi, right? Like 22/7. But we have to remember, those are just convenient rational stand-ins. They're close, but they're not exact. The true value of pi can never be pinned down by a simple fraction. Its digits just stretch on and on into infinity, a completely chaotic, non-repeating sequence that has absolutely fascinated mathematicians for centuries. All right, next up in our irrational zoo is Euler's number, E. This is another one of those fundamental constants that just seems to pop up everywhere in math and science, often in the most unexpected places. You can think of E as the secret ingredient for continuous change. It's woven right into the fabric of mathematics for anything that grows or decays smoothly and constantly. We're talking about everything from the way interest compounds in your bank account to how biological populations expand. And for our last example, we've got the golden ratio phi. You might have also heard it called the divine proportion. Now, don't let the name fool you. Even though it's called a ratio, it's not a ratio of two simple integers. This number has captivated artists, mathematicians, and thinkers for centuries because it just seems to show up everywhere, in the spiral of a seashell, in the petals of a flower, and supposedly in the pleasing proportions of great art and architecture. So now that we've met a few of these different characters in the irrational zoo, we can finally start to appreciate the modern and, honestly, kind of staggering understanding of where they fit on the number line. Okay, get ready for a fact that might just break your brain a little bit. It feels completely counterintuitive, but there are infinitely more irrational numbers than there are rational numbers. Yeah, think about that. Both sets are infinite, sure, but the infinity of rational numbers is countable. That means, in theory, you could start listing them all out. But the irrationals, they're uncountably infinite. It's a completely different, bigger, denser, more mind-bending kind of infinity. Here's a way to picture it. Imagine the number line stretched out in front of you. The rational numbers, they're like an infinite sprinkle of fine dust. There are countless points for sure, but there's always a gap between any two of them. The irrational numbers, they are the line. They're the continuous fabric that fills in every single one of those gaps and connects everything. So let's wrap this up. What are the big takeaways from this deep dive? Well, first, irrationals are the numbers that just can't be written as a simple fraction. Second, their decimal expansions are endless and totally non-repeating. Third, we learned their discovery, starting with the square root of 2, caused a massive philosophical crisis for the ancient Greeks. Fourth, they come in two flavors, algebraic, like the square root of 3, and transcendental, like pi and e. And finally, and this is the really wild part, these strange numbers actually make up almost the entirety of the number line. They're not the exception, they're the rule. But let's end on one final provocative thought. Even after thousands of years of study, the number line is still full of profound mysteries. We've walked through the proof for the square root of 2, right? But for another really important number, Euler's constant, also called gamma, well, mathematicians still have no idea if it's rational or irrational. We just don't know. And that really leaves you with the sense that the story of numbers is far from over. It's still being written.